Good afternoon, ladies and gentlemen. Welcome to the second edition of IIIT Bangalore's public lecture series, Bangalore on IT. Yes. On behalf of IIIT Bangalore, I'd like to take the opportunity to thank you all for coming here and being present here today. Before we begin, I would like to introduce you all to Bangalore on IT. As some of you might know, Bangalore on IT is our institute's public lecture series. The current version of this event started in January 2019 with an objective to introduce eminent and accomplished thought leaders working on cutting-edge topics to our students, IT professionals, and the general public at large. First event had Dr. Marianne Maas, Professor of Organizational Behavior at HEC Lausanne in Switzerland, give a talk on virtual reality. Today, in our second edition, we have Professor Ravindran from IIT Madras, who is here with us today to give a talk titled, Why the Recent Excitement in AI. To introduce the speaker of the day briefly, Professor Ravindran currently heads the Robert Bosch Centre for Data Science and Artificial Intelligence at IIT Madras and is one of the foremost reinforcement learning experts in the country. He is a professor at the Department of Computer Science and Engineering and is the co-director of the Reconfigurable and Intelligent Systems Engineering group at the same institute. Professor Ravindran received his PhD from the University of Massachusetts Amherst and his master's in research degree from IIT Bangalore, and has over 2 decades of research experience in machine learning and reinforcement learning. He has, in the past, held visiting positions at IIT Bangalore and University of Technology in Sydney. Professor Ravindran is one of the founding executive committee members of the India chapter of ACM Special Interest Group on Knowledge Discovery and Data Mining, and is currently serving as a chapter president. His research interests are centered on learning from and through interactions and span the areas of complex network analysis and reinforcement learning. Today, Professor Ravindran will be speaking on 2 paradigms that underlie much of the modern success in artificial intelligence, especially in the last 1 decade, one of them being deep neural networks and the other reinforcement learning. Professor Ravindran today will touch upon the biological motivation of these 2 paradigms and will explore issues surrounding the implications and failures. I would request our director, Professor Sadgopan, to say a few words on this occasion.
When you have a distinguished speaker, the last thing to do is to give a few words, okay? All that I will do is I'll hand over the bouquet and then invite Professor Ravindran. Yes.
Good afternoon, folks. And so I'm going to talk on why the recent excitement in AI. But there's an alternative title to this talk which I have used before, How Human is AI, right? So what I'm going to try and do, this being a public lecture, I'm not going to get into equations and stuff. So anyone who has seen me teach classes on YouTube, don't worry, no equations are going to pop up anytime. And oh, I take it back. There are some equations, but that's so simple that I don't call them equations. So AI is hot, whether it is playing games, right, or whether it is popping up on your Facebook and telling you who your friends are. And I'm pretty sure a good fraction of the population here talk to AI more often than they talk to other human beings, right? So it's there everywhere, right? So AI is amazing, right? But at the same time, you also have people who say that AI is going to kill you. And so remember this quote by Elon Musk. I'll show you another quote later, right? That if at the very least should convince you that Elon Musk has split personality. Okay, but then it's really not true, right? Obviously, so all of us know that AI is not going to kill us because we can always turn off the machine, right? So, but then don't just take my word for it. A recent survey of 50 Nobel laureates ranked climate, population rise, nuclear war, disease, selfishness, ignorance, terrorism, fundamentalism, and even Trump as greater threats to humanity than AI. Okay, so we have quite a ways to go before get that, right? So what's the talk about? I'm going to have like 2 or 3 slides on trying to tell you what AI is, basically tell you that no one knows, and then move on to talk about a little bit more concrete things as to why people are getting so excited about AI nowadays, right? So I mean, a good number of people in the audience, for them, all this excitement about AI is deja vu, right? So people have seen this happen in the 80s, right, like early 90s, right? I'm pretty sure there's no one in the audience who saw this happen back in the 50s, right? The AI excitement. So it's not the first time that AI is popping up in the radar, and so let's see why we are getting so excited about it again. But then first off, what is AI, right? So these are like multiple different definitions. There is really no one definition of AI, right? There's nothing that says this is AI. In fact, a good number of people who are disillusioned with AI say that AI is nothing but a marketing slogan. There's nothing really called AI, right? But then you can broadly, I'm not going to read out the definitions. You can broadly think of this as, okay, systems that think like humans, systems that act like humans, right? And systems that think rationally, systems that act rationally, right? So in fact, if you go to this side of things, it's more closer to game theory, right, than to AI. But then some people claim that game theory is also part of AI, right? So it's like I said, there is no one good definition. So let's not really worry about defining what AI is. But then let's go ask questions about, hey, why this excitement about AI, right? So let me read this. Navy revealed the embryo of an electronic computer today that it expects will be able to walk, talk, see, write, reproduce itself, and be conscious of its existence. Wow. Amazing, right? But this is from 1958. Right, so this is an article about Rosenblatt's perceptron from 1958. But what I found really funny is the second quote, right? It can tell the difference between a cat and a dog. I mean, what is up with cat and AIs? Right, so we were all excited about, I mean, Google being able to find cat videos, right, on YouTube. Right, so I don't know how many of you remember that. I mean, some of you in the audience look young enough to have not been around when that happened, this was like 10, 12 years back. So, okay. Anyway, so why again now? Right? So I picked this. I was at some meeting, and then there was all this pamphlets some company was handing out, and this was the catchphrase from that headlines. This is I saw this in September 17, 2018, and look how remarkably similar. We're able to walk, talk, see. Machines can now see, think, and talk. Literally, we have gone back to the 50s in terms of the excitement about AI. Right? So what's really happening? Right? So. In some sense, I would say it all started with this ImageNet competition, right? So the goal here was that I'm going to give you a set of images. So I'm taking your advice and pointing to the middle screen, right? So I'm going to get a set of images, and each image is going to come with a label. So these are all airplanes, these are all automobiles, these are all birds, and so on and so forth. Just from this kind of a label data, can you learn to identify objects from images, right? So that's basically the task, and it turns out to be a very challenging problem for computer vision, learning from scratch. Okay, so people thought, okay, we have to do a whole bunch of reprocessing, we have to define features, we have to think about how humans, recognize images, and so on and so forth. A lot of work went into this, and people were working very hard to solve this problem, right? And then somebody came up with this quote-unquote deep neural network. I'll tell you what it is a little later. And then they started getting very good performance and much better than the state of the art, right? And then year after year, the performance kept getting better and better until they reached a point where they were building a system that had about 3.6% error rate. What is amazing about it is because on the ImageNet data set, when they have humans try to solve it, humans have a base error rate of about 5%. So they basically got superhuman performance, right? So always keep at the back of your head what I said about marketing, right? So they're basically getting superhuman performance now, and that kind of kicked off entire excitement in AI all over again, right? And then to add to the marketing fuel, you had things like AlphaGo, right? So Go is an interesting game. So that chess has been solved by AI a long time ago, right? So we heard in the 90s we had chess playing programs that was beating Garry Kasparov, right? And one of the things I remember from the 90s was that we all felt very proud for a brief while, because the computer program that bet Garry Kasparov lost to Anand. Right? So we all said, good. At least there's something which Indians are. Okay, fine, let's not go there. So then we had chess has about a branching factor of 35. So what do I mean by that? So at any given board position, right, you have to consider on average 35 possible next moves that you could make, Go, on the other hand, has an average branching factor of 250. Right? So on an average, you have 250 possible moves that you might have to examine to continue playing. So the classical AI techniques which use the search-based, exploration, really couldn't scale to Go. And at some point of time, Go was considered like the final frontier of AI. See, so this is something that you really need to have knowledge. You have to understand how humans think so that you can solve Go. Right? And then these guys from DeepMind built this AlphaGo program, which is a Go player that literally learned from some amount of past history, but also learned largely by self-play, right, playing against itself. And then it managed to come to a point where it beat the 18-time world champion, Lee Sedol. He was widely regarded as one of the strongest players to have played the game of Go, right? And so when they actually started the tournament, right, head-to-head tournament with Lee Sedol, DeepMind was making all the right noises, saying, "Oh, we hope we don't, make a fool of ourselves, and we put up a strong performance, etc., etc." And by the time the fourth game in the series rolled around, and Lee Sedol actually won, right, people were very surprised. Oh my God, he managed to win. Because the first 3 games, AlphaGo played so well that from the computer beating the human being a surprise, just in the space of 3 games, human beating the computer became a surprise, right? And to the best of my knowledge, this is the last publicized event of a human beating AlphaGo in the game of Go. So after that, all the other games it has played against humans, it has won by X to 0 margin. So much so that the newer versions of Go, they didn't even test against humans. They just tested against the old version of Go. As far as Go testing was concerned, humans are redundant, right? So anyway, so that created a lot of buzz. So much so that there's even a documentary on this. If you haven't seen it, I recommend it. So it's a very well-made documentary. It has won several awards for filmmaking. Not for the AI part of it, but for the filmmaking, it has won several awards. It's a very well-made documentary, so do get a chance to catch it. And of course, there are more game-playing things. I'll move a little faster on the games, of course. Oh yeah, no, I had to go back. This is the place, the split personality. OpenAI is first ever to defeat world's best player. So he's so happy that AI works, right? That's Elon Musk. And then earlier you saw quotes about AI coming to kill him. So anyway. So, but not just fun and games, right? So people have also solved more serious problems, and so Google used the same engine that played Go, right? And with some little tweaks, got it to control the power consumption in their data centers, right? And managed to reduce the power consumption by up to 40%, right? This is really, really wonderful because Google data centers consume more power than small countries. Right, so the fact that they were able to save power there, it is actually amazing, right? And the more recent big ticket story, which is not game playing, I mean, there are a couple of more game playing bus stories out there. Is a thing called AlphaFold, which is again a variant of the same. In fact, I take it back. It has nothing to do with the AlphaGo engine that won the game of Go, but then Alpha had become a trademark now, so they made it AlphaFold. Which is for protein folding, and in the last year's protein folding competition, the AI agent achieved a 25% improvement over the nearest performing human. Right? The humans are typically clustered together in 3, 4, 5% improvements each, right? But then this guy kind of blew away the field, right? So people start thinking, maybe there is something to it, right? So what exactly is different? So I'm going to show you some pictures now, right? So you can think of old AI like this. It's a fancy driver, okay, and driving a car like that. All right. So, and what is new AI? New AI is this: the same fancy driver driving a much more fancy car. Right. So, what does this car give you? It gives you a better engine, right? More compute power, and it also can consume more fuel, which is data. So, literally, the data is the fuel for all these AI algorithms, and the compute power is the engine. And it's not like the algorithms haven't changed, they've become slightly better, so wearing fresher clothes, but more or less the same thing, right? So to make it a little more concrete, so what I mean by more fuel, I mean data, better engines, I mean compute powers, right? And the thing that's really taking advantage of the confluence of the algorithms, power and data is essentially what are deep neural networks. Okay, and so of course I have to pay homage to these people because they got the Turing Award this year. So that's the innovations, most of the methods and algorithms that went into making deep learning a huge success story were driven by these three people: Joshua Bengio in Montreal, and Jeff Hinton at Toronto, and Jan LeCun at New York. And the three of them were jointly awarded the Turing prize this year, right? And so what has this allowed us to do? It has allowed us to achieve superhuman performance in variety of things, right? So I already showed you about images where we said superhuman, right? And now we have the speech recognition accuracy. So that line up there was the human accuracy on recognizing speech, right? So of course we know that humans make mistakes, right? We only hear what we want to hear, not what is said, right? So, but discounting for that, right? So humans on a standardized test set make a certain error rate, and of course computers are getting up there, right? And of course now so much so that we have all this voice assistants and all the commercial grade products that thrive on speech recognition that are out there, right? But I do have a funny story about Alexa. So we have an Alexa at home, and we also have a yoga teacher who comes weekly for classes, right? And whenever the yoga teacher comes and says exhale, right, and Alexa hears it as Alexa for some reason, and then tells us, I don't know how to do that. So it became so annoying that we actually have to turn off Alexa whenever we have the yoga classes running. So superhuman performance. Right? But then not just these kinds of practical applications. I mean, people have managed to get neural networks to do something really artistic. Right? I mean, of course, art, creativity are all in human endeavor, right? So machines can never do that. So this is basically an input to the neural network, a style in which to paint, and a picture, and then this is what it produces, right? So the picture recolored in the style that was given to you. Or you can give it a sketch, give it a doodle, and it gives you money. Right? Well, at least a passable imitation of one, which I can't tell apart, right? So, of course, and then these are all snapshots which were colorized by a deep learning agent. The black and white pictures that were fed in, and then it outspits color things. And it's gotten to the point where the NeurIPS conference is the #1 neural network conference, started running an annual art competition for AI. Okay, so people actually make entries, and somebody recently set a record for the highest valued painting, AI painting sold, and yeah, marketing, things are going crazy, right? And let's look at another example where things have been. Now I'm going to slightly make things go downhill. Okay, so amazing. Give this picture, and then it produces a caption that says a person riding a motorcycle on a dirt road, right? Or a group of young people playing a game of frisbee. Great. And then 2 dogs play in the grass. Okay, fine. 2 hockey players are fighting over the puck. Okay. Well, you can't really see the puck in the image, but what else are hockey players going to fight over? Right? So we can excuse it. But then, a skateboarder does tricks on a ramp. That's not a mistake you're going to make. You're not going to call somebody who's driving a 2-wheeler bicycle as a skateboarder. Right? And then a little girl in a pink hat blowing bubbles. Okay. That's a little harder to get there. But then, just not this, right? So things can get really bad. So that's a panda. Right? I add some noise to it. And what is that? Obviously a gibbon. Right? And a school bus, I add some noise to it. Surely an ostrich, yeah. Right? And the dog, another species of ostrich, yeah. Right? So these are things that, that kind of show how fragile some of the state-of-the-art neural networks are, right? So we say that, hey, we are getting superhuman performance, but then it's all very carefully controlled environments. But still, there's a lot of excitement in AI because, we are now seeing products, right, that are using AI. Right? Okay, I'll come to this point a little later. Some more examples. This is a language generation problem. So I'm trying to translate from this source, which I believe is German, to English, and this is the best translation engine produced. So you can see that the protest that began on Thursday at 6:30 before the McDonald's at McDonald's at McDonald's. No, it's not echo. It's not, so it just made a mistake and then just keeps repeating the same phrase because whatever is the computation going on is essentially is not letting it move beyond producing McDonald's as output. So these are all things that you wouldn't expect a reasonable solution to make, right? This mistake is a reasonable solution to make, right? But despite all this, there's a lot of buzz. So one of the things reasons behind this buzz, right, is the fact that the technology is maturing to a point where we are no longer just satisfied with it working, right? So we have started asking other things of it, right? So for a large fraction of my research career, and we are just happy to have any AI thing work, right? I'll be happy if I get my AI agent to play tic-tac-toe, right? Finally it worked after 10 weeks of simulation time or something like that. So now those things have become almost commonplace, right? In fact, at this point of time, I expect my AI to work than not expect my AI to work, which is what it was till a few years back, right? And therefore, I start asking it other things like like reliability, right? All the kinds of performance measures, right? So and apparently this thing is known as the ELITs of engineering. So I got for reliability, scalability. So all those additional things, not just something that functions, but I'm going to ask for more guarantees from the system that functions. And I guess we are coming to a point where we're beginning to ask these questions of AI, and AI doesn't have answers for it yet, right? So we, as researchers, also are struggling to say, okay, we really have to solve these things if we want more wider acceptance, right? So we'll get there, right? So the first thing I was going to talk about are deep networks. So the deep networks are, I'm pretty sure most of you are aware, are based on this notion of an artificial neuron, right? The idea was that you have all these inputs that come into a neuron, and somehow that neuron does some computation and then produces an output, right? This goes back to 1943. The model itself is a very highly simplified model of how biological neurons act. So the roots of deep networks actually go back to 1943. It's not anything. So 68 itself was like a second generation of things, if you will, right? So what are exactly the biological inspiration that we are taking from this? So there are three things where we actually look to biology to give us AI, right? So we're anyway talking about intelligence, and the model of intelligence we have is humans, right? And of course, there's also this famous quote about the previous generation's chess playing in Deep Blue, right? Because Deep Blue does not, they use a search to play chess, right? And so somebody was making this comment to say that Deep Blue doesn't think about chess. It's like saying that an airplane doesn't fly because it doesn't flap its wings, right? So there might be different ways of solving them. This is the thing about acting rationally, right? Acting like humans. We may not necessarily think about humans, but of course, but AI did take a lot of inspiration from biology. So I'm going to talk about that part of it now. So the three components here. That is the neuronal structure itself, right? Like I showed you the McCulloch's neuron, and then the macro architecture. So how do you hook up these neurons together? And the last one is how do you actually get these neurons to learn something, this network of neurons to learn something, right? Don't worry, I'm not going to take a class in neural networks or anything. There's more pictures. Some of them pretty, some of them not, right? So one of the earliest neuronal architectures was the one of perceptron, right? So it's almost like the McCulloch's model with some differences. So I have inputs, and then they pass through some weights. These are like the synaptic connections in neurons. And then you take a weighted sum, and if the sum is greater than the threshold, the output of 1. If it's less than the threshold, the output is 0, right? So this is the very simple, the basic computing unit. Okay. So this is the one that you saw the news item about. Okay. So perceptron was the one that they were expecting it to do all these fantastic things. Okay. So, but anyway, so what did we do? So there is this a basic structure. In fact, the basic structure hasn't changed. Okay, that basic structure is still intact. What has evolved over time is the threshold function. Instead of saying if it is greater than a threshold, output of 1, if it's less than a threshold, output of 0, people said, oh, no, I'm going to make it soft thresholds, right? So as it approaches the threshold, I'll switch from 0 to 1 or -1 to +1 and so on and so forth, and we call the neuron as firing. And this made it easier for numeric algorithms to work, to train the neural network, as opposed to having a threshold, which made it harder for you to do certain computations. But already we have taken one step away from biological realism. But nowadays what people do, they came back and figured out, hey, this thresholding thing is what is preventing you from doing really well in training. Right? So one of the insights that allow us to do so much better nowadays with neural networks is actually moving away from the soft threshold and moving to something called a rectified linear unit. Right? And the rectified linear unit essentially says, okay, if your output is positive, if it's greater than 0, then output a scaled version of it. If the output is less than 0, either you don't output anything or you output a highly attenuated version of it or something like that. And this allows you to train much more efficiently, but at a cost of biological realism. So to get better and better performance, we're moving more and more away from biology, even though we were originally motivated with from biology. And of course, the network itself, the meta structure we're talking about, right? So you have single neurons, but you want to go to deep learning, so you put multiple layers, and that's how our brains are also organized, right? We have layers and layers of neurons that do computation. So people said, okay, let us do layers and layers of neurons, right? But then they also looked at other ways in which the brain operates, right? And I can't even pronounce these brain regions. I'm pretty sure some of you can recognize these off the bat. But the idea here is that there are parts of your brain that have very limited receptive fields. They don't look at the entire input, right? They look at some fraction of the input, and then they do computations on that. And then depending on which part of the input that you're looking at, you detect various kinds of features from that, and then use that in doing the computation. So what did people do? They said, this is the right thing to do. And then they built something called convolutional neural networks that operates with limited receptive fields, right? And convolutional neural networks are not new. They go back to the 80s again, right? The first convolutional neural network, which Yann LeCun is well known for, goes back to the 80s, right? But then he couldn't get it to work at really large scales, and that needed to wait for AlexNet, which is a form of a convolutional neural net in the mid 2000s to happen, right? So basically, the idea here is you have layer after layer after layer of this limited receptive field, and what do these do? So the first layer of these filters basically respond to certain orientations, lines, gradations in color, and so on and so forth, right? And then second layer starts looking at little bit more features like corners and edges and maybe color conjunctions, two colors together, and so on. These are the kinds of features. You can't visually recognize them as meaning anything yet, but these are building blocks on which you're going to start looking at things like textures now. So these are some similar kinds of textures and so on and so forth, right? And then you put together these textures and start recognizing object parts, right? So faces start showing up, and there are legs that start show up. So different filters start recognizing different things as you keep going deeper and deeper, and then finally you start recognizing entire objects, right? And then you basically say, hey, that's a dog, and this is a cat, and so on and so forth. So this is essentially how the convolutional networks operate. And what was amazing about all of this is that I don't have anything explicit that tells me that you have to find faces here, you have to find edges here, you have to find colors here, and so on and so forth. That somehow seems to organically fall out of doing this training. And of course, I always jokingly say that if you go near a deep network and sneeze, its performance might change, right? Because all of these are very finely dependent on starting conditions and your rate at which you are doing the adaptation, and so on and so forth. But then with a few attempts, you can get this to work and do really well. And then, of course, you get these kind of wonderful superhuman performance. But then to get to that 3.6 performance, the number of layers it used was 152. Okay, I probably need a much larger head to hold a brain that has 152 layers, maybe not. Maybe not. I mean, nobody knows how the brain is connected, right? So there is this theory that our cortex has a 7-layer structure, and then we start off at the 7th layer and then have connections going back to the 1st layer. So literally we are stacking seven layers on top of each other. So it's quite possible that even within our brain we have not infinitely, but indefinitely deep networks, right? Not just 7 layers or anything. We're not really limited by the physical layering, potentially, but we don't know. But still sounds pretty biologically implausible for me, right? But of course, this is little older results. People have now managed to achieve the similar kinds of numbers with a lot fewer layers, with better training and better hardware and so on and so forth. But still, the point is, we are no longer motivated by biological realism. We're just happy to get performance. Of course, let's not blame AI for that, right? So that's just standard IT problems. Yeah. So it started off with learning with neural networks. Started off with variants of what is called Hebbian learning. So Hebbian learning says that, okay, if the input was active and the output was active, then you should increase the association between the input and the output, right? So that's basically like co-firing or of input and output should drive the learning, right? But then nowadays it's predominantly driven by error gradients. So you look at your prediction, you have some errors, then you back propagate the gradients or whatever, right? And it's not even clear if there are the pathways to back propagate gradients in the brain. I mean, there are some theories either one way or the other, but nothing concrete. But we still achieve superhuman performance, right? We don't care about this, but we also fail spectacularly, right? Like the gibbon there. So I'm pretty sure most of you fail to recognize the gibbon, right? And so that's the thing, right? So we have a lot of excitement, but huge pinch of salt. Okay, great. So the second success story, or second reason behind the success story is reinforcement learning. And this is something close to my heart. Okay, so it pains me, and I'm bleeding internally while I'm going to say bad things about RL also to you. But
so in fact, I wanted to ask you about your opinion of Jan LeCun's statement, right, about reinforcement learning being the cherry of the cake.
Hey, who would make a Black Forest cake without the cherry? Right, the cherry is an integral part of the Black Forest cake. Yeah. No, well, kidding apart, I don't think you can really split apart. Okay, this part is unsupervised, this part is supervised, and this part is reinforcement learning. I think the neural networks in our brain are trained using all kinds of signals. Right. In fact, I have started using this term omnivorous learners because we should not be just limiting ourselves to saying that I'm going to solve this problem using supervised learning. And so, in fact, case in point, there is this very strong game playing engine that somebody built. And the reason they were able to build it with very little training data is that they used reinforcement learning to learn the control law. But for learning what features they should use for representing the control, they actually use supervised learning. So the same neural network was trained by a supervised signal and by a reinforcement learning signal, and it learned to play a game much faster. So I don't think you can, there's nothing like a cherry. If you pull the cherry out, you're going to get a chunk of the cake with it. So yeah, I disagree with the statement. I disagree with the analogy itself. Yeah. Anyway, so all this learning things I was telling you about all involve some kind of data, right? Some kind of label data. So this is a question I ask. I think I've been doing this for 15 years now. So how did you learn a cycle? Right? Certainly not from data. Right? I can now that with YouTube I can show you 100,000 hours of somebody riding a cycle. Right? I can probably get you 1,000 hours of the same person riding the cycle also on YouTube. Right? If I search hard enough. But then you still won't be able to learn the cycle. You can watch how many ever videos you want. You have to get on the cycle and try things out. You don't know how the system is going to react. So this is all a trial and error learning. And this trial and error learning is something that is very ingrained in us, right? So we know falling down hurts, and so we don't want to fall down, usually. But then this is not just cycling, I asked cycling because many of you would remember learning to cycle, right? I could have asked about walking and talking, right? I don't expect anybody to remember how they learned to walk, right? But if you have babies in the house, you have seen how they learn to walk. It's all a trial and error process, right? So you have to fall down, right? So that's why babies' bones are rubber. You know, they vulcanize over time, right? They start off as rubber so that they can fall down, trial and error, and then walk, talk, etc. So what is reinforcement learning? Is essentially a mathematical formalism of this trial and error learning paradigm. So literally, you're learning from rewards and punishments, and so the way to think of what reinforcement learning does, right? It gives you feedback. Supervised learning also gives you feedback, but supervised learning tells you what do you have to do, right? So the feedback is more of instructions. It says if this is the input, you have to tell me it is a cat. If this is the input, you have to tell me it's a dog. It gives you instructions, right? Well, reinforcement learning says, hey, you do something, okay, and then I'll tell you whether it's good or bad. It's evaluation. You start riding the cycle, okay? If your uncle claps, then you're doing a good job, right? He's not going to tell you how to ride the cycle, right? So that's basically it. You get evaluations. Right? Learning from evaluations is what reinforcement learning is. Learning from the instructions is more of what supervised learning does. And the goal, of course, is to learn some kind of long-term performance. You learn to maximize some kind of long-term performance. The crux is you learn about the system through interaction, right? If anyone was paying attention for my overlong bio, towards the end it said, this is what I'm interested in, learning through interaction, right? So that's what reinforcement learning is all about. You have to need a system that you have to you are interacting with, and you learn from that. But surprisingly, or not so surprisingly, reinforcement learning is inspired by human intelligence. It all goes back to behavioral psychology. So people remember Pavlov, have heard of Pavlov's dog, right? So what does a Pavlov's dog do? So dogs normally salivate when you get to see food, right? And what Pavlov did was he basically, whenever he presented food, he rang a bell, and soon the dog started salivating when you ring the bell, right? So this is called a conditioned reflex, right? So the salivating on seeing the food is a unconditioned reflex because it's getting ready to digest the food, right? But then when you start salivating on the bell, it's a conditioned reflex because it's learning to anticipate the food, right? So this kind of association of outcomes to stimulus is one way of the very simplest form of reinforcement learning, right? So how do you learn to associate this to? So this was called it's called conditioning, right? And there are a whole variety of different kinds of conditioning experiments that people ran. And there is a very simple mathematical formalism called the Rescorla-Wagner rule. It's nothing but a linear function approximator, if you will. So I have stimuli, which is represented by U, and W is an association of stimuli to payoffs, and V is the predicted payoff, right? Predicted rewards that I'm going to get. And a lot of these phenomenon could be modeled by this kind of a linear rule, and that just uses the error and updates it, right? So as time goes by, your weight actually goes to the expected reward. So basically the rule you learn is if the stimulus is present, then this is the expected reward. Very, very simple rule. Like I said, right, I wouldn't even call it an equation, right? So, but then it modeled a whole bunch of different things. So acquisition is what Pavlov's dog experiment told you, right? Extinction is essentially if I keep ringing the bell but not give the food, I'll stop salivating when the bell is rung. Okay, that's called extinction. I no longer have the association, right? And blocking is okay if I'm already salivating at the sound of the bell, right? If I start flashing a light also, right? I learn no association with the light. So every time I'm going to give you food, I first flash a light and ring a bell and then give you food, right? But I already have learned the association between the bell and food, so I'll not learn any further association between light and food. So this is called blocking. So the bell blocks the light, right? So this is another thing that people looked at, and a whole bunch of other things, right? Inhibition, overshadowing, etc., etc. And all of this, right, was adequately modeled with that simple linear rule that you saw, which is the Rescorla-Wagner rule. But there is another phenomenon called secondary conditioning, which essentially goes like this. So the dog is already trained, okay? It salivates on the bell ringing, okay? Now what I do is I flash a light a few seconds before the bell rings, right? And then I ring the bell, and then I give the food. Now the salivation transfers from the bell to the light. This is called secondary conditioning. Okay, and how much it transfers depends on how strongly I associate the bell with the food, not to the presence of the food itself. That's why it's called secondary conditioning. I've already done my primary conditioning, which is to associate with the bell. The secondary conditioning takes me to the light. And this could not be modeled using the Rescorla-Wagner rule. You needed to start having a notion of time, right? And then you did something like a convolution to predict the reward. So look at the stimuli over the last few seconds, blah, 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 and so on and so forth. So people had to come up with a new model for describing this, right? So this is, in some sense, one of the reasons why people looked at the most popular reinforcement learning paradigm, which is called the temporal difference learning. So I'm going to use the next few minutes to kind of give you the intuition of what temporal difference learning is. And we'll use the game of tic-tac-toe, right? So anybody here bored enough on playing tic-tac-toe already? No? Okay, I'm presuming all of you know tic-tac-toe. And the supervised learning way of getting an artificial agent to play tic-tac-toe would be something like this. Remember the instruction versus evaluation part. So the instruction part will be something like, hey, these are possible positions you could be in, and this is what you have to do in those positions. Right? I'll give you sets of pairs of these kinds of moves. Right? So position, move. Now I have to learn from this instructions I'm giving you and start learning to play the game of tic-tac-toe. And what is the reinforcement learning way of doing it? A second, just play the game. Right? At the end of it, if you win, I'll give you a point. If you lose, I'll give you -1. If you draw the game, I'll give you 0. Now somehow learn to play the game from this. No instructions, only evaluations. And not only do I give you evaluations, I give you delayed evaluations. You have to play the full game and then I'll tell you whether you won or lost. Right? So I don't tell you along the way which move was good or bad. Right? How do you learn from this? Of course, I can't do this by playing the game once. I have to play the game repeatedly, so I have to learn from repeated play. So let's look at a very simple way of doing it that you can implement with matchboxes. Right? It's called menace. Menace stands for, yes sir.
Taking a tic-tac-toe analogy, what happens if you're biased towards one of the classes in the sequence?
Sorry?
What if you're biased towards one of the classes more than the other?
What classes? There are no classes here. I just have to win the game.
Okay, so your reward.
Yeah.
So most of the time you end up in a drawing. Right?
Potentially, yeah. If your opponent is playing an ideal game, yeah. So tic-tac-toe, don't take tic-tac-toe too seriously to heart. Okay, just an illustrative example. So if you want to use tic-tac-toe as a serious thing, then assume that your agent opponent is playing a quasi-random game or something like that. But just an illustration. Okay. I'm not going to use reinforcement learning to solve tic-tac-toe. It's too simple a problem for me to solve. Okay? Yeah. Don't take it too seriously. Yeah. Anyway, so how do you do this? Okay. So the matchbox educable knots and crosses engine. Right? It's a menace. Right? So this is a menace that has plagued machine learning and AI for a long time, coming up with all kinds of crazy acronyms so that your algorithm sounds cool. Right? Anyway, the idea here was you have a set of matchboxes. Each matchbox corresponds to a board position. Right? You can see that position written out here. Right? Each matchbox corresponds to board position, and each of the matchbox has beads of different colors, and each color corresponds to a particular move that you could make in that position. Right? So here there would be beads of 3 different colors. So each color would correspond to one of these moves that you could make. Right? Make sense? Okay. Now, when I'm playing the game, whenever I come to a particular position, I open the matchbox, take out the bead of that color, take out a bead of some color, and then make the move corresponding to that. And I'll remember the bead I took out. Right? And then I play the whole game. At the end of the game, if I win, for every matchbox I opened in the game, I put back 2 beads of the color I took out. If I lose, I throw away the bead. If I draw, I put back the bead that I took out. So essentially what have I done? Whenever I win the game, I increase the probability of playing that move again, because I put back 2 beads of the same color. So the next time when I draw a bead at random, the chances that I'll draw the same bead goes up slightly. Right? When I lose the game, I throw away the bead. Therefore, I decrease the probability that I'll play the move again. And if I draw, I leave it unchanged. Now, if I play this game repeatedly, right? I'll eventually gravitate towards moves that cause me to win more often than not, right? So this is a very simple way of learning how to play by repeated things, right? So one way of thinking about it is, hey, I have this all potential things that tic-tac-toe can happen, and I play a game, right? If I win, I go back along the path and increase the probability of all the moves that I took along the path. If I lose, I decrease the probability of all the moves. If I draw, I leave it same. Okay? Do I have to wait till the end of the game? So what about a position like that? Do you think I have won? Maybe, as long as I don't lose my mind, right? So I probably the X can win from here. So I don't have to wait till the end of the game to know that I have won. From here, I can basically change the probability of taking the previous move. I say, hey, look, you've gone to a winning position already, increase the probability of this move, right? So I don't have to wait till the end. But that's a trick here, is how did I know that this was a winning position? You know the rules of tic-tac-toe, right? So you can kind of make a guess, hey, from this point you can't lose. But then tic-tac-toe, as I said, don't take it too seriously. So tic-tac-toe you can recognize by visual inspection whether you have won or not. But in reality, how would you do that, right? So just purely of learning by repeated play, what you could do is, for every move, you can keep a track of how many games have I won after seeing this position. Right? So every move I can keep a track of how many games have I won after seeing this position. Right? Now, when I make a move, I go from a position that has a, say, 60% chance of winning to a position that has a 80% chance of winning, then I can say that's a good move. And I can automatically increase the probability of making that move. I don't have to wait till the end. Right? And I can in fact do that along the way, everywhere. Likewise, if I go from an 80% chance of winning to a 30% chance of winning, I decrease the probability of taking that move. Right? So this is basically the idea that, hey, I'm just going to look at what happens one step down the line and use that prediction, right, in order to update my values at time t. So look at the predictions at t plus 1. Prediction here is what's the probability of winning. I'll use that to update my value at time t. Okay, and so this is called temporal difference learning. Very simple rule, and so this is how it looks like in the notations that I skipped over very quickly. So I'll not go over it again. But this was originally proposed as a behavioral psychologist tool, right, to explain secondary conditioning. And then, of course, they used it to also do a control problem. And so the first paper, which is typically attributed to temporal difference learning, is by Bartow, Sutton, Anderson back in '83. So it's Bartow, Sutton, and Anderson. And it's had profound impact, not just in AI, but also in behavioral psychology, computational neuroscience, and other places. And yeah, so in the interest of time, I'll skip this, except to tell you that not only is this at a very high level an accurate model of how animals learn, but there is some biological relevance. These are actual dopamine recordings made when a monkey was learning to solve a task, and the way the dopamine signals vary, right, seems to indicate a similar kind of variations as in the temporal difference error. So the TD algorithm, how it changes over time, right? The dopamine signals also seem to vary like that, right? That doesn't necessarily mean that they are solving, monkeys are using TD learning, but given the volume of experiments that has happened over the years, right, repeatedly under various conditions, and always the TD errors seem to predict this with very, very good accuracy. Therefore, it's widely believed that primates use, or animals, right, use temporal difference learning as well. And like I said, it's got a lot of influences. It started off with behavioral psychology, neuroscience, AI, operations research, robotics, optimal control. A lot of fields have fed into reinforcement learning and in turn have taken influences from RL. But unfortunately, nowadays it's more and more on AI, right, and optimal control and operations research, and less on the biological underpinnings. We are moving into more and more optimizable algorithms, efficient implementations, etc., etc. And so RL is behind much of the modern success stories, and it has moved on to now a deep neural network, right? So instead of looking at those simple equations, which we didn't want to call as equations, it's gone into this full-blown hardcore gradient-based learning. And so solution approaches no longer biologically inspired, but then they do solve really amazing problems, right? In fact, all of these success stories I told you earlier, so many of the success stories I showed you earlier, were all enabled by an RL engine sitting in there somewhere, starting from AlphaGo, AlphaFold, everything. And the new generation of AlphaGo is something called AlphaZero, and it's not just a pure RL algorithm. It has a whole bunch of other things that go into it, but it's a single algorithm that can play things like chess, shogi, and Go. And notice the marketing term used again. And it uses no human data. It trains completely from scratch. And in fact, the Go game does all kinds of crazy things. In fact, one of the commentators who was watching the AlphaGo Lee Sedol game actually made a comment that it felt like he was watching an alien intelligence in action, because they were not able to explain what the AI was doing while the game was going on. And then later on, people went back and said, oh, okay, that is what he was trying to get at. Right? Moves that were specifically prescribed against when they teach you to play Go, it actually used successfully to win the game. Right? So this is something that is amazing. And of course, AlphaZero beat that AlphaGo agent that beat Lee Sedol 100-0. See, they don't have to play against Lee Sedol anymore, right? So they just play against AlphaGo. And yeah, so it's amazing. But then that's a humanoid trained using reinforcement learning. Doesn't look like very human-like learning, right? It's like basically doing this while it is running, right? It looks like yeah. So Rajinikanth chasing after villains or something. Hey, stop here! I'm going to kill you, right? So that kind of a move there. But it turns out it's actually a valid thing. That gives it a counterbalance. That rotating thing. So it makes it easier for it to balance and run. But it doesn't sound like a very human thing to do. But anyway, so RL has its own problems. So what is AI good at? So things that we should be selling AI for: games, of course. Interfaces. AI is amazingly good. Hey, it's okay if my Alexa tells me it doesn't know how to exhale. Right? That's not really causing me too much loss or pain or anything. So it's fine. I'm happy to use interfaces. Right? And of course, we know that it's getting superhuman performance. So I'm pretty sure that there is some human there who thinks exhale as Alexa. And then, of course, image tagging. A lot of success stories in image tagging. In fact, that is one of the biggest medical success stories as well. Looking at image segmentation, looking at radiology images, ophthalmology images, and so on and so forth. That AI seems to have had good success. And of course, it has to be non-adversarial, right? Remember the gibbon and the ostrich, right? So as long as you're looking at natural images, it's fine. But if I start looking at face recognition for some kind of authentication to open up your secret vault, right? Don't buy the product yet. Okay. And chatbots, of course, right? So everybody uses chatbots, but still in a limited setting. I can't have a general knowledge chatbot yet, but it has a long way to go to human performance. Right. Having said that, and especially in the context of something like autonomous driving, like people talk a lot about cars running around and things like that. So you have to ask the question, when I say human performance, which human am I talking about? Okay. So here was a study that was done by MIT Media Lab. It's like a generalization of the moral machine thing. So you're driving a car, of course, you're being irresponsible and driving very fast, and suddenly you find some pedestrians crossing the road. So you have two options. Either you can just run into the roadblock here and stop, right, causing severe injury to your co-passengers and yourself, or you can swerve. So little skulls on top of the pedestrians. You can swerve and hit the pedestrians and save people in your car. What do you want to do? No, I'm not asking you the question. Okay, so I mean, given the levels of road rage that exist in Bangalore, I don't want to ask the question. But then it turns out the answer is not as straightforward as you think, right? So look at this. So people from Japan, Norway, and Singapore were placing more emphasis on sparing pedestrians, right? And the least emphasis on sparing pedestrians with China. Maybe there are too many of them, right? That's why I don't want to ask the question in Bangalore either, right? And Estonia and Taiwan, right? And similarly, most emphasis on sparing the young. Right? I mean, there are a lot kinds of things. Like, what if they are old people? What if they are young? What if there's a light that said don't walk and they are still on the road? right? Or is it okay because they're breaking the law? Obviously, they're evildoers. Okay, let's run them over, right? So is it okay for you to do that? So all kinds of variations, right? So then people ask more emphasis on sparing the young. France, Greece, Canada, UK, right? The least emphasis on sparing the young. Taiwan, China, South Korea, surprisingly Japan, right? Yeah. No, India was not part of the. Sorry. Yeah. So luckily. So nobody can make jokes about Indians. No, nobody can make jokes about Indians having too many people running over them and stuff like that. So, but anyway, the point is, so if I want to build an autonomous driver, right, autonomous driving vehicle, so which human do I model it? So should I change it from market to market? So in China it is okay to run over pedestrians, but in the US you have to stop when somebody wants to cross. Yes, which human-like is not even a well-defined goal, right? Yep.
So you mentioned that reward and penalty depends on the outcome of the decision.
Yeah.
If you are able to say they're successful, you give a reward.
Uh-huh.
If it is not successful, you give a penalty.
Maybe.
But if you are not able to find out whether it is successful or not, then all these methods fail.
No, that's a different thing about it, right? So if you're going to talk about how humans decide where rewards, what are rewards, right? So there is no separate reward channel for humans, right? So I'm just taking in the visual output coming in from outside, right? Yeah.
You can say that if you fall, then it is bad.
Yeah. Hey, if I'm a masochist, I'm not sure about that anymore. I might want to fall and get hurt a little bit. Yeah. It depends on my value system, right? So see, I'm not even talking about where the rewards come from. Where the rewards come from is a huge open question. Right? But when I'm engineering solutions using RL, then I know exactly where the rewards come from because I know exactly what I want to achieve. When we start moving more into the psychology side of things, then you have a whole bunch of other things. You have to talk about primary drivers. The real reward function is, okay, am I satiated? Right? The primary drivers, right? So food, like roti, kapda, makan, those kinds of the primary drivers. So that is essentially what my rewards should lead to eventually. But then how I interpret what the world is giving me is significant individual variations. In fact, the problems with your dopamine system is what leads to addiction, right? What leads to schizophrenia. Right? So in fact, okay, let's take this offline. I can tell you a lot more about all these dopamine problems and how our reward system gets screwed up, right? But the point is, yeah, so when you're talking about humans, it's very hard to decide where the rewards come from. When you're talking about engineering systems, you can have well-defined cost functions, and you can define.
You mentioned something about we hear what we want to do.
That was a joke, but anyway, yeah. But still, it's true, yeah.
So I'll try to put this question here. What it actually helps us is our sense of self. We have our own sense of self, self-interest, and intention. So is that what is even missing in autonomous driving? That is, can you create cars that are more moral and less different sense of personality? Which you can use for different kinds of driving.
Hey, were you a fan of the Herbie movies as well?
Sorry?
No, I don't know. People who watched movies in the 80s might remember the Love Bug.
Yeah.
Cars with personalities. I'm talking about. Yeah. Sure. See, if you can tell me computationally what is personality, then I can tell you whether my machine has achieved it or not. Right? Otherwise, it's open to interpretation. In fact, you would impose your views of what the machine is doing on it. Right? The machine itself, as of now, I don't know that if there is a computational theory of personality. Yeah, or self. Yeah. Even we can talk about this. Yeah, later. Yeah. So I have 2 more minutes. Oh, okay, fine. Yeah, sure.
No, I just wanted to add, whenever we build product, we always put it for a customer segment, for a market. So obviously there's no one solution fitting all. So it has to be customized. So that is when we...
Oh, for the moral machine stories, eh?
Yeah,
sure.
So
but
when
people are not talking about it, right? People are just talking about, human-like AI. They don't say that, hey, no, human-like, this is human, that human. They're not talking about that.
But then they have to specify their subject, like what was their qualification, what was their background, what was the gender, and so on. So that is when we become more specific about which human.
Yeah, I completely agree with you. But also there's a slightly more subtle issue here. I don't think if you had stopped the people and asked them, hey, do you prefer pedestrians over people in cars, they would have tried to put on their moral hat and give a different answer. So only when they put a gun to their head and said, okay, do one or the other, they actually chose this, right? So yeah.
The point is again, the answer that you give and what you do is again they are two.
Yeah, completely agree with you. So there's a lot more subtle issues here, and I'm just saying that from the AI point of view, people have not looked at those questions. They have not asked those questions. They just, yeah, we are still happy that our AI works, right? We are still not gotten into the elitities of it, like I said earlier, right? So yeah, it's still there. So this is good point. It leads me to this slide. AI is still like a kid, right? So yep.
Yeah, I have a question.
But then the next two slides have to come together. So I'll go back. Yeah.
Okay. My question is, in the computation we have this computability test, like NP complete test. So like that, is there a way of predicting whether AI is applicable to a particular class of problem?
I don't know if there is a way of characterizing applicability of AI yet. Right? I mean, people always say there are engineering issues. I mean, do you have enough data, and so on and so forth. Yeah. So any problem? For example, people have trained a neural network to do addition. So why would you want to use AI to learn addition? And just for the heck of it, right? So people have you can train a neural network to learn how to sort numbers. I mean, these are you would think these are algorithmically well-defined problems. Why should I want AI to do it? So I mean, if you want to do it, yes, you can try to build a data-driven way of solving things. Whether it will be efficient, whether it's good or bad, except in under very simplifying assumptions, very strongly simplifying assumptions, people don't have good theoretical answers for that. Right? So that's the way. Anyway, so going back, AI is like a kid, right? But more like this kid. Right, so you have to be very careful about using AI, right? Use the kid responsibly, and don't blame it, right? If the skunk goes up in flames, right? So summing up, really a lot of excitement in the AI community, right? So all of you are here, so that sense is outside the AI community also excitement, but there's a sense of responsibility, right? So we have to start asking all the hard questions now, right? And in fact, if you go to many of the AI conferences, people start talking about regulation of AI. And in fact, I heard a really, in one sense, funny, in one sense, disturbing thing, that the state of California is now trying to come up with regulatory laws, but a separate set of laws for AI and a separate set of laws for ML. Right? So I don't know how they're going to distinguish. Anyway, fine. But then this is the message, right? We are closer than ever to functional AI, right? AI is now starting to affect people. But then the caveat is, again, because we taught this in the 80s, we taught in the 60s that we are close to functional AI, and we saw that, right? 58, right? We were having a reproducing computer, etc., etc. So we have to make sure that we don't lose sight of what is true. And again, need to focus on building human-like AI, which is explainable. The AI should be able to convince me that it's doing the right thing. It should explain to me and convince me it's doing the right thing. It should be robust. It should be agile. And I also have another bullet which I didn't put it up here because, yeah. So you know that AI is beginning to affect people at a large scale. You know why? So politicians and lawyers are talking about AI now. So you know the AI has arrived. Right, so use it carefully. Thank you.
Just talking about AI and cryptography, I was just wondering, why is it that AI has so much trouble in performing a simple task like XOR or something like that?
Not
like
anymore.
Why does neural networks?
Not anymore. You have to
issues?
update your neural networks from the 1960s. Yeah. AI hasn't had trouble with XOR since the 1980s.
But it has had trouble with like secure computing on secure data.
Meaning?
Meaning like sorting on encrypted data and stuff. AI has been.
I think Quicksort has problems on sorting encrypted data, right?
Yeah,
so I mean, if you're going to encrypt data, that's a whole set of different problems, right? So I don't think it's a particularly AI issue. So And the reason it becomes more important with AI is because AI relies so much on data, right? So, and people are not happy sharing data. So you have to figure out ways of working with encrypted data. But that's not the normal mode of operation yet, right?
Okay.
So everything has problems with encrypted data, not just AI.
And one more question. Do you have equally strong theoretical guarantees that RL will converge to an equilibrium as you have in the case of neural networks with Sabenko's theorem?
Neural networks and what?
And Sabenko's approximation theorem.
So you have strong theoretical guarantees for RL under certain assumptions, right?
Like?
But if you're going to run, well, no functional approximation, for example,
Okay.
and enough samples and appropriately cooled learning rates, etc., etc.
Correct.
But then if you start doing any kinds of nonlinear functional approximation like neural networks, there are no guarantees.
As we conclude today, I would like to thank the director, the deans, the registrar, CAO, facility team, administration, the housekeeping staff, team security, and the branding committee, and all of you present here today for making the second edition of Bangalore IIT a success.